I realized after finishing the video, the last video, that I actually did not get in the last slide here for beta radiation. So we'll go ahead and do that one real quickly, and then we will move on to gamma radiation. So the last little bit here on beta radiation. Beta radiation does not have as much ionizing power as alpha radiation. It does not have as much energy, and the main reason for that is just because it's not as big. A beta particle, an electron, is much smaller than an alpha particle, which is the helium nucleus. It's much, much smaller than a helium nucleus. And so simply because it's smaller, it doesn't have as much energy. It's like, if you get, if somebody shoots you with a BB, it's gonna hurt, sure, but it's not gonna hurt really badly. That's like a beta particle. On the other hand, somebody throws a bowling ball at you, that's going to hurt a little bit, just because it's so much bigger. It has a lot more energy. So despite the fact that it is so much smaller, making it have not quite as much ionizing power, it does have better penetrating power than alpha particles do. What that means is that you're not going to be safe with a piece of paper between you and a beta emitter. The beta particles, because they're so tiny and because they're so energetic, they can actually travel through materials a lot easier than alpha particles can. Some of them will be shielded by the paper, but the majority of them will not. The majority of them will actually travel through very thin, low-density materials like that. So, in other words, if you're not a long distance away or have a sheet of metal, which is much higher density than a piece of paper, between you and the beta emitter, then you are in trouble. So, moving on to another type of radiation that can be emitted by a radioactive source, and that is gamma radiation. This is completely different from the previous two that we've looked at, because gamma radiation is actually electromagnetic radiation. It is not actually releasing a particle with mass in the way that we think of it anyway. Technically speaking, photons can have mass, but for our purposes, they do not have mass. This is just a high energy photon is all this is. It's a very, very high energy light that is being emitted with gamma radiation. And as I say here, when I say high energy, I am not kidding. They are very, very short wavelengths, and they are deadly. These are the most difficult to shield yourself from because it's light, and it's very high energy light. Light can travel through materials, and we should be very grateful for that, by the way. Otherwise, we wouldn't be able to see anything at all. But light is able to travel through certain materials. So light can travel through atmosphere, for example. Light can travel through water. Certain wavelengths of light can travel through some stuff and not through other things. Believe it or not, like water, we think of water as being clear, and it's clear in the visible range, but actually water is not clear in other ranges. There are other in the, I believe, the IR range, the infrared range, water actually absorbs infrared radiation, if I'm not mistaken, which means that if you were some kind of an animal that could see infrared light, and that's what you use to see, you actually wouldn't be able to look through water. Water it'd be like looking at like a piece of paper or something that's opaque. You wouldn't be able to see through it. So gamma radiation is high enough in energy that it can pass through practically anything. You need a lot of shielding to protect yourself from gamma radiation. Gamma radiation most often occurs with other types of radioactive decay. It can happen all on its own as well. So you could just have some kind of maybe uranium-235 that for some reason is at a really high energy, and it could decay and still just be uranium-235, but release a gamma ray, release a gamma photon. and it just ends up at a lower energy. Things like that do happen, but most of the time when gamma radiation is occurring, it's because there's other stuff happening as well. So, for example, when uranium-238 decays via alpha decay, so it gives off an alpha particle, the thorium that's left behind has to kind of rearrange its protons and neutrons. It has to shift things around inside of the nucleus, and in doing that, it gives off a gamma ray, or maybe even 2 or 3, just depending. Every nuclear decay is not identical. There is a little bit of variation. So gamma radiation actually does technically have the lowest ionizing power of all the types that we're going to look at. So each gamma photon has less energy than a beta particle, and it has less energy than an alpha particle. However, it has by far the highest penetrating power, which makes it really difficult to shield yourself from. And so usually this is the one we actually worry about the most. Because again, it's relatively easy to protect yourself from the other two, especially alpha particles. It's relatively easy to protect yourself from it. Gamma radiation, you have to have some pretty serious shielding to be able to work with something that's really what they call a hard gamma emitter. There are certain isotopes of certain elements that are termed hard gamma emitters because they give off a lot more gamma radiation than other radioactive isotopes. And if you're going to work with those kind of things, you literally cannot work with them in the same room. Like, you have to have the material in one room with a robot, and you are in a different room on the other side of the compound, working the controls to use the robot to work with that material. It's very dangerous. Plus, it turns you into the Hulk, but only in the MCU. It's a caveat there. Only in the Marvel Cinematic Universe. It will not actually turn you into the Hulk in the real universe, our universe. It will just kill you. So do not try to turn yourself into the Hulk. The last kind of radioactive decay that we're going to look at is positron emission. This kind of decay is exactly the same as beta decay, with one exception. The one exception is that the particle that is emitted is positive in charge instead of negative. Everything else is exactly the same. Everything that's going to, like the size of the particle, the overall, if you don't take into account one is negative and one is positive, the size of the charge, all that is the same. The only thing that's different is the thing you're shooting out now has a positive charge, and so you're kind of doing it backwards from what the beta emission was. So a positron is just a positively charged particle. It is kind of the twin, essentially, of an electron. Has the exact same mass, the exact same charge. It's just positive instead of negative. And so when we have a positron emission, we're going to turn a proton in the nucleus into a neutron, which again is just the opposite of what happened with the beta emission. In that one, we turned a neutron into a proton. And so now we're going the other direction. And actually, let me go ahead and try to find an example of that for you before we call it a day, or at least call it a video. Let me see here. I thought I had an example in there, but I guess not. So there's beta decay. Okay, here we go. So this is example 17.3 in the book that I'm using right now, which the example number might be different depending on which edition of the book you're using. But we're going to write a nuclear equation for the positron emission of potassium-40, and we're just going to go and do it here. So we have potassium-40. Again, that 40 is the mass number. If we look at the periodic table, potassium has an atomic number of 19. Because we know it's undergoing positron emission, we know one of the products is going to be this. So again, it looks just like a beta particle, and so we go ahead and give it the same symbol, the E for electron, except it's not actually electron, it's a positron. But it has no mass number and +1 as its atomic number because it has the same charge as a proton, but none of the mass of a proton. To figure out what the other thing must be, which is really the one thing that we have to kind of work out here, because we're already told that we have potassium-40, and because it's positron emission, this has to be the other product. The only thing that's really unknown is this second daughter nuclide. We know that it has to have a mass number of 40 because there's no mass change. When it loses that positron, the positron does not have a mass number associated with it, and so 40 has to be the mass number. And given the fact, if you remember from the last video, the atomic numbers here have to be the same from one side to the other. They have to sum to the same number. So we have 19 atomic numbers on the left. We need 19 on the right. Because we already have 1 accounted for here, that leaves us 18 here. If you want to think about it differently, you can think about it in terms of for positron emission, you're always going to be turning a proton into a neutron, and so you're losing a proton here. We're going from 19 down to 18. And if you look at the periodic table, I believe that is argon? Yeah, argon. So we turned potassium into argon with this positron emission. So any kind of positron emission, if you're writing the nuclear equation for that, it's going to be very similar. You're going to have some starting material. It's going to release a positron, which has a mass number of 0, atomic number of 1, and then the other daughter nuclide you can work out just by keeping in mind that all the mass has to still be there. So we have 40 on the left, 40 on the right, and then 19 on the left, 19 on the right. So you can work those out. So the next slide here is just kind of a summary table to kind of give you something to come back to when you're working through the homework and stuff like that. And you can look at these, and it explains what each one of these types of radioactive decay, what they're doing in each one, what kind of particle is produced, whether they have high or low or moderate ionizing power and penetrating power, and then it gives you an example of each one. So this is kind of a handy little table to come back to when you're working on things. I'll see you in the next video.